So welcome to the video. Today we're going to take a look at how to do an independent t-test on version 31 of SPSS. So normally we're going to use this test when we have an independent categorical variable comprised of two levels and when we have a continuous dependent variable. And for this example we're going to imagine that we're looking at the body weights of male and female 12-week-old mice, and we're going to use the test to see whether there's a difference in their body weight. So in this Excel file, a 0 represents males in this sex column and a 1 represents females, and in this body weight column we have their weights in grams. So let's take a look at how to put these data into SPSS. So we will go to variable view and then we'll give a name to the independent variable using this name column here. So let's call this one sex. And then in the row below, let's give a name to the dependent variable. So we're going to call this weight. Then we're going to use this values column here to specify what the different levels of the independent variable are. So if we click on the cell here in the sex row, and then on this box here, we can tell SPSS that a 0, so I've just clicked on that plus button, a 0 equals male and a 1 equals female. So once this looks like this, we can go to OK to close this. Then we can use this measures column to indicate that sex is a nominal variable, which is similar to a categorical variable. And we can use this measures column to specify that weights is a continuous or scale variable. Then we can go down to data view and we'll see that the names of those two variables appear at the top of these two columns. So then we can just copy and paste our data from this Excel file into SPSS. So I'll select the top left piece of data, I'll scroll down and then I'll click the bottom right bit of data while holding Shift to select all of the data. Then I'll go to Command or Control C to copy the data, go back to SPSS and I'll select the top left cell to copy and paste the data in using Command or Control V. And we can see that we have male and female in this column here rather than the zeros and the ones that we had in the Excel file, and that's because in this view menu we have value label selected. If we unselect it, we just see the numbers instead. So this test has a couple of assumptions. So one of them is that there is a normal distribution within each of the groups, and the other is that there is homogeneity or variance. And as I've said here, if you find that these assumptions are not met, you might consider doing a Mann-Whitney U-test instead, which is the non-parametric equivalent of the independent t-test. So we can check this homogeneity or variance assumption as we run the t-test, but we should check this normality assumption before running the t-test. So to do this, we can go up to Analyze and then down to Descriptive Statistics, then across to Explore. And then we can transfer our independent variable to the factor list, and then we can click on Plots. I'm going to untick Stem and Leaf, and I'll tick Histogram, and I'll tick Normality Plots with Tests. Then I'll go to Continue, and then I will go to OK, but first I just need to transfer this dependent variable over to the dependent list. And then I'm just going to scroll down slightly until I get to this test of normality table. And this table actually contains a couple of different normality tests. So we have the Kolmogorov-Smirnov test and we have the Shapiro-Wilk test. Normally when we have fewer than 50 data points, we use the Shapiro-Wilk test, and we use this test on the left when we have more than 50 data points. We can see here that we have 25 males and 25 females, so I'm going to focus on this part of the table. And the most interesting thing is the sig column. So we can see that for males we have a sig value of 0.103, and for females we have a sig value or a p-value of 0.202. So these are both above 0.05, and in the case of this test, that indicates that these data are normally distributed in both groups. You can also look at the histograms to try to get a sense of whether the data are normally distributed. So if you have a normal distribution, you should see a sort of symmetrical bell shape in your histogram. However, if you don't have many data points, often these histograms don't look very convincing, which is actually the case here. There's not really an obvious sort of bell shape, and I would tend to favor these tests of normality instead because they provide you with a more objective threshold for determining whether or not your data are normally distributed. i.e. is the sig value above 0.05. So now that we've checked that assumption, let's get on to running the test itself. So we can go up to Analyze and then down to Compare Means and Proportions, then over to Independent Samples t-test. Then we can transfer our independent variable to the grouping variable box and our dependent variable to the test variables box. We also want to check this homogeneity or variance test option, and the last thing we need to do is click on our independent variable and then on Define Groups. This as a default comes up with 1 and 2, but we actually used 0 and 1 to represent males and females respectively. So I'm just going to replace 1 and 2 with 0 and 1. Then I'll go to Continue, and then I'll go to OK to run the analysis. And if we look at this group statistics table, we can see that we have a mean of 26.52 for the males and a mean of 24.28 for the females, suggesting that the males tended to be heavier than the females. However, we need to look at this table here to determine whether that difference is significant. However, before doing that, let's actually take a look at this homogeneity of variance test table. So this contains Levine's test for equality of variances, and for this we want to see that we have a sig value above 0.05, as that indicates that we have met the assumption of homogeneity of variance, which essentially just means that the data are spread out to a similar extent in both of the groups. So here we have a value above 0.05, indicating that that assumption has been met. And whether or not that assumption has been met determines which of these rows in this table here you should look at. So here it says equal variances assumed. So we are assuming equal variances because this value is above 0.05. So I'm going to be focusing on this row here. However, if you saw that your sig value was below 0.05, you would instead focus on the numbers on this equal variances not assumed row. So I'm going to focus here, and specifically I'm going to focus on this one-sided P column. So you can either look at this one-sided P column or at this two-sided P column. And which you look at depends on whether you have a one-sided or two-sided hypothesis. So a one-sided hypothesis in this case would be something like it was hypothesized that males would be significantly heavier than females, whereas a two-sided hypothesis would be something like it was hypothesized that there would be a significant difference in the weights of males and females. So the one-sided hypothesis is more specific than the two-sided hypothesis. So I'm going to imagine that we had a one-sided hypothesis and we were predicting that the males would be heavier than the females. So here we can see that we have a P or sig value of less than 0.001, and as that is less than 0.05, it indicates that the males were significantly heavier than the females. So that's how we interpret the results of the independent t-test. But let's now take a look at how we can write up those results. So I have an example here, and I've said that an independent samples t-test was conducted to compare the weights of male and female mice. So that sentence obviously just says why we did the test. Then I've referred to these Shapiro-Wilk tests, and I've said that they indicated that the data were normally distributed among the males and the females. And then we have these statistics here. So these are coming from this table we looked at earlier, this test of normality table. So we have a value of 0.93 after W. So W is the Shapiro-Wilk value. So if we look at this table here, we can see in the statistic column, we have a value of 0.933. So I've just rounded that to 2 decimal places. We have a degrees of freedom value of 25, and we have a sig value or a p value of 0.103. So that's what we have here. We have this 25 is the degrees of freedom, and then we have this p or sig value, which is 0.103, and then we've just done the same thing for the females over here. So those are just these statistics here. So next I've said that Levine's test indicated that the assumption of homogeneity of variance was met, and then I've included these statistics here. So we have an f value of 2.57 and a p-value of 0.116. So if we scroll down, we can find this table called homogeneity of variance test, and here we have these values. So 2.57 rounded to 2 decimal places and 0.116, so that corresponds with what we have here. And then we get on to reporting the results of the t-test itself. So we've said that compared to female mice, and then we've reported means and standard deviations for the female mice. The male mice were significantly heavier, and then we've reported the results of the t-test. So let's take a look first at how to report these descriptive statistics. So for the female mice, we have a mean of 24.28, and that's coming from this group statistics table where we have this female row and a mean of 24.28, and we have a standard deviation of 2.42, which is what we've got here. And then we've got the same thing for the male mice. We've got M, or mean, equals 26.52. That's coming from here. And the standard deviation is 1.81 if we round that to 2 decimal places. And that's what we have here. And then we have the results of the t-test. So we've said that t equals 3.71, and that's coming from this independent samples test table. And I'm looking at this equal variances assumed row and at this t column here where we have a value of 3.71 rounded to 2 decimal places. We have a degrees of freedom value of 48, which is what we have in brackets here, and we have a p-value of less than 0.001, which is what we have here. Lastly, I've said that the effect size was large, and I've reported a Cohen's d value of 1.05, and that's coming from this independent samples effect sizes table. And I'm looking at this Cohen's d row and at this point estimate column where we have a value of 1.048, which we would round to 1.05. And I've described that as a large effect based on these criteria here. So I've said that Cohen's d values between 0 and 0.2 represent very small effects. Those between 0.2 and 0.5 represent small effects. Those between 0.5 and 0.8 represent medium effects. And those above 0.8 represent large effects. And I've described here how those same criteria apply if we have a minus symbol before the Cohen's d value. So here we have a value of 1.05, and as this is above 0.8, I've described that as a large effect. So that's about it for the independent t-test on version 31 of SPSS. If you have any questions, just let me know in the comments and I'll try to get back to you. Thank you very much for watching, and I'll see you next time.